Okay, so we're now going to return to this idea from the last topic that we were kind of leading towards at the end there, right? About the interactions between these two magnetic fields. Which two magnetic fields? Well, the external one that was already there, and the induced one that was created by the current, which of course the current was itself induced by the external magnetic field and a moving charge within that magnetic field as a result of the resulting magnetic force. Okay, so now we're going to get just a little bit more, a deeper understanding of why the current induces in the direction it does. Of course, it is because of the magnetic force, as we already kind of understood. But another reason, let's say, of why that kind of has to be the direction in which the current is induced, or the electron flow, whichever one you're looking at. So I want to return now to this question that was at the bottom of the page. It said, compare the direction of the external magnetic field to the induced one in each of the previous examples. So let's just come back to these really quick. We had drawn them out last time. Okay, I just want to remind you, if you're doing your hand rules here, you will notice that on this side, right, if you take your first hand rule for a straight electron flow, you'll notice that over here, your fingers are curling out of the page, okay? Now, I want you to take a second and think about this. So imagine, let's go back quickly to our two parallel conducting wires, right? What would two parallel conducting wires like this do? Well, they would. What would two parallel conductors like this do? Well, first, what would the electron flow look like for both of these? Well, take your left hand. If the if the if the magnetic field is out of the page for this guy, then that must be the electron flow, and conversely, for this guy, it might be that way. So do you remember two parallel conductors? How will their magnetic fields interact? They'll interact in such a way that they will repel, right? So we kind of have a similar scenario going on here. We have a magnetic field out of the page and a magnetic field out of the page. And just for another really quick visual, if you imagine your eye was down here, and so you were looking this way from the side, what would you see? You'd have your wire here from this angle, but it would be going away from you, and the electrons would be flowing into it, right? So an X, and the magnetic field around it, well, you can see it's going down over here, and then up here it would be going kind of up, right? Of course, because if you do your left hand rule, the magnetic field looks like that, right? Okay, what would this look like? Well, this is just kind of a straight magnetic field. So over here, you would just have basically a straight arrow up. So again, why will these repel? Because of the interactions between the magnetic field. But if you like, we can use our replacement magnet method to kind of explain why this happens, right? So what I mean by replacement magnet method is just take this point here, literally a tiny point, and say, what kind of bar magnet would we put there to get the same resulting magnetic field at that tiny little point in space? So I'm drawing it this big. Remember, it's really just that infinitely small point there. What could I replace it with? Well, I could replace it with magnetic field lines are entering down here, so that must be a south. And up here, that must be a north. So the induced magnetic field at this point is the same as if I just had a tiny little bar magnet that looked like that. What about this one over here? So if I replace this one with a tiny little bar magnet, right? Again, it looks like it is entering a south and leaving a north. So hey, if these two bar magnets were next to each other, what would they do? Would they attract or repel? We got a north next to a north and a south next to a north, so those would repel, right? That also kind of, we didn't touch on it too much back when we first did the parallel conductors, but that works for this too, right? If you don't believe me, try redrawing it. Take your perspective down to where this eyeball was and look at this one, and you'll see that you get the same kind of result. So just a quick kind of touch up on why those things will repel by visualizing what bar magnet would kind of give us the exact same magnetic field at the points where they are closest to each other, where they are interacting the most heavily, right? And so these will repel each other. Now, what was the initial change in magnetic field that the wire experienced, right? Because remember, when that wire moved through a magnetic field, current was induced because a changing magnetic field can induce a current, or in this case, we were talking about electron flow, but similar ideas, just different hand rule, right? And so again, that initial change in the magnetic field was by pushing the wire this way. And we said that this is going to lead to repulsion, right? This induced magnetic field on this side, that would lead to repulsion. Okay, so that would be the opposite of what we tried to do with the wire, right? In other words, the induced current was induced in such a direction that it resisted the change we tried to put into place, right? We tried to change the magnetic field by pushing the wire this way, and the induced magnetic field interacted with the external magnetic field in a way that gave us repulsion. It resisted our trying to push those together. Okay, looking at this one here. What change did this magnetic field, this external magnetic field, cause in our charge motion? You can see that it was kind of curling this way, right? And so this thing's magnetic field was kind of constantly changing because it's put on a spiral path. Now this induced magnetic field on the inside, what kind of change? Let's just pretend these were all dots because that's what this is here. How would that cause it to curl? Well, take your right hand, flip it around, now point your fingers out of the page instead of into the page, and you'll notice that it would curl the other way. So again, it's kind of acting, this induced magnetic field is acting to do the opposite of what the original change in the magnetic field was doing, right? So compare the direction of the external magnetic field to the induced one. Well, it always acts to resist the original change in magnetic field, right? As we just kind of saw in those two examples, without even thinking about it too hard, just using our hand rules. We kind of said, hey, it seems like it's always acting to resist whatever change in magnetic field it's going through. Now, this is actually basically a statement of something called Lenz's law. So I'm going to show you something really quick that might help you kind of wrap around why Lenz's law. So Lenz's law already kind of, as we've seen, makes a good amount of sense just based on kind of almost deriving it from our hand rules like we just did. However, there is another very important reason that Lenz's law really does have to exist, even without our physics 30 understanding of hand rules and directions based on those. So I'll show you what I mean really quick. Okay, so to show you what I mean, I want you to consider two objects that I have here. I have just a normal pen lid, okay, and I have a neodymium magnet. Okay, so again, neodymium is a mineral that is ferromagnetic. It's a permanent magnet. Okay, its electron shells are filled in such a way that their magnetic poles don't cancel each other out, so that the atoms overall have a magnetic field, and then domains can have a magnetic field, and all the things work out so that this is a fairly powerful permanent magnet. Okay, so you can see it's sticking to this filing cabinet because the filing cabinet is also ferromagnetic. The pen, of course, pen lid is not. So, as you know from physics 20, even though this one's a little bit lighter, mass doesn't actually make a difference in how quickly things fall on Earth, right? Air resistance can, but if things are the same shape, the mass doesn't actually have an effect on how quickly they fall. So, to demonstrate that, let's take a look. All right, pretty much land at the same time. Okay, in free fall, they're hitting at the same time. Now, I'm going to drop this non-magnetic pen lid through this thing. Okay, so this is an aluminum tube. Aluminum, by the way, also not magnetic. I'll show you that in a sec. So I'm going to take the pen lid and, okay, not that exciting. It falls through. You can watch it fall through. Okay, in fact, it kind of falls through so fast you can barely see it go through. Okay, like I said, here's my neodymium magnet, right? It's definitely magnetic. It's sticking to stuff. Okay, there it's sticking to the side. But look, not magnetic. Aluminum is not ferromagnetic. It will not be attracted to even a powerful magnet like a neodymium magnet. Okay, you need two magnets or two ferromagnetic materials at least to do that. However, when I drop it through, okay, there's no tricks here. No tricks at all. So again, side by side, if I drop it outside of the tube, and if I drop it in the tube. Now, it's not because it's sticking to it on the inside, right? That can't be what's happening. So what is happening here? Well, I want you to consider this. What kind of energy does this magnet have right now before I drop it? Well, it has potential energy. In physics 20, if I asked you as it falls, what kind of energy is it going to gain? It's going to gain kinetic energy, right? It's going to be moving faster and faster and faster. Okay, we know the law of conservation of energy. Energy cannot be created or destroyed, but it can change from one form to another. So this potential can become kinetic as it falls if I do it outside of the tube. Now this is a magnet and it is moving. This is made of metal. It might not be a ferromagnetic metal, but it's still a metal. What is metal good at? Conducting electricity. So I have a magnet with a magnetic field that is moving near a conductor. So electromagnetic induction, Faraday's law says that in the conductor, if I have a changing magnetic field, there should be an induced current in that conductor. Okay, Now, which way is the current going to be induced? We have a kind of a circular conductor here, right? So we kind of have two options. It could be induced this way, or it could be induced that way. To first think about this, we're gonna need to think about the field of this. So let's first determine what that is. So I'll try and keep it steady there. Okay, so, field line's pointing in, so that must be the south, right? Just to confirm. Yes, pointing away there. So north is down right now, south is up. Okay, north down, south up. So now, when I drop this magnet with its own magnetic field, I now have a changing magnetic field in a conductor, right? So let's just think about the two options here, right? Current could go that way, and if current goes that way, then, okay, now current will induce its own magnetic field, and which way does our second-hand rule say it will be? It says it would be, the north would be down here in our induced. Okay, so if north would be down here, that would mean south would be up here. And what do I have? I now would have a magnet with its north pole. If north is down here, then south is up here. What would those two magnets feel? Well, they'd feel attraction, right? And so that would act to speed up the magnet. Now let's go back to what I was saying about energy. It's going to go, it has potential energy. It's going to induce a current. So now there's actually electrical energy, and it's going to get sped up even faster than it would have just fallen due to gravity. So you're going to get more kinetic energy out than you put in potential, and you're going to induce electrical energy along the way. Does that sound possible, or does that sound like it violates the law of conservation of energy? You bet it violates the law of conservation of energy, right? So for that reason alone, we're kind of forced to think the current must be induced the other way then. It must be induced in such a way that the magnetic force, the result of the interaction between the changing magnetic field of this thing falling and the induced magnetic field from the induced current from the changing magnetic field from this guy, must act in such a way that the north pole down here is meeting a north pole in here. So as this north is up here, it meets a north and they repel, and it acts to slow it down. It's kind of just a consequence of the law of conservation of energy. Pretty cool. So for another quick kind of demo of Lenz's law in action, right, I have here two more neodymium magnets. You can tell they're neodymium magnets because they're very strongly attracted to each other and to my filing cabinet. They're actually so strong that they're kind of annoying to get apart. Okay, and then I have here two tubes. One is made of PVC, right? So essentially plastic, okay? And then I have a copper tube. Now copper, it is a metal, but it is clearly not ferromagnetic, right? That magnet does not even want to stick a little bit, okay? So do you think Lenz's law will be apparent in the PVC? Now why or why not? Or do you think it'll be apparent in the copper, okay? What would be the difference between those two things? Well, copper is a metal. Copper is a really good conductor, right? It's actually most of what we make most wire out of is copper. When that changing magnetic field from the dropping magnet travels through this copper tube, right, it is a good conductor and it will allow a current to be induced in itself. However, PVC is an insulator, right? Plastic is definitely an insulator, so that will not allow it to happen as much. So I'm going to drop these two magnets at the same time. Okay, hopefully you can at least hear it. I don't know if you'll be able to see it very well, but just, so here they go. Can you see that? Just to kind of show it from above as well, because it is quite cool from above. Okay, I'm just going to drop it in. Cool, right? It's almost like it's just kind of levitating through, which it basically is, because of the interaction of the external changing magnetic field and the induced magnetic field. This kind of resistance to a change in a magnetic field by the induced magnetic field in the induced current is what kind of actually makes a lot of technologies work, like a maglev train, a magnetic levitation train, right? That's all based on Lenz's law. A metal detector actually uses Lenz's law. So again, Lenz's law, when a changing magnetic field induces a current, the induced current is always in a direction so that its induced magnetic field resists the original change in magnetic field. So let's just come back to this a bit. Think about, okay, great. So a induced current will always be in the direction so that its resulting magnetic field resists the initial change in magnetic field, right? So That's what it's saying here. When a current is induced by a magnetic field, okay, its direction is such that the resulting magnetic field, the one induced by the current, is opposite of that of the magnetic field that caused it, or at least opposes the change. So the result of this is that the magnetic field will always act to slow down the motion, never speed it up. Remember, if it sped it up, you would violate the law of conservation of energy. You'd be getting more out than you put in. So in simple terms, if a magnet's moving to the right, okay, the induced current will cause a magnetic field that will at least try to push the magnet to the left, right? It will slightly push the magnet to the left. It will never also push the magnet to the right, okay? So let's look at this. So honestly, what does Lenz's law change for us? Really not a whole lot, okay? There's just this kind of extra little hoop that we're going to jump through at the beginning, which is, okay, if I move the magnet like this, how will the induced current move so as to resist it, right? Or you can think of it as what kind of magnet needs to be there to resist that change in the magnetic field, okay? So that's it. And then once you've done that, it's just plain old regular hand rules that we're used to, okay? So if this is actually not really a question the way it is, right? The way it is, it's kind of just diagrams about Lenz's law. Let's pretend like this was a diploma question and they maybe didn't give us the arrows. So let's just pretend that's our question and we're teachers marking this and we're going to see how this student did, okay? Can let you know now they're going to get 100% because these are just diagrams showing Lenz's law, but let's approach the questions that way so we're actually doing them as questions, not just some pictures. So, like I said, first things first, how would you resist that change? So the V of the magnet is in. It's moving towards this solenoid. So how do you resist something coming towards you? You repel it, you push it away, right? So how do you repel this north pole? Well, you get a north pole close to it and you get a south pole away from it. You can't just magically have a north pole, right? You've got to have a south pole on the other side, okay? So again, that north-south didn't just kind of magically appear to resist. I mean, it does need to resist because otherwise the law of conservation of energy would be violated, right? But something induced those north and south poles. What did it? Well, let's actually figure out here what this arrow is, okay? So be careful here. I know this looks like it's saying that's the positive terminal of the battery and that's the negative terminal of the battery. This is a resistor, not the symbol for a battery. That's a symbol for a resistor. So it's not actually going to mean the same thing here. So just maybe go ahead and ignore those because it's not really important for this course. Okay, now let's see. If I'm north has to be this way, right? So what is that arrow? Aha, that arrow must be, if in the front it's going down, thumb points towards north, right? Right thumb points towards north. We have a curly current. So this is our second right hand rule, okay, for a straight magnetic field and a circular current. So this shows I. What did we do differently than we would have always had done? We just had to figure out, okay, where's north and south going to be based on resisting this change. So if you bring a magnet towards a solenoid, it will induce a current that resists that motion. Okay, let's look at this one. Now they're taking a south pole and they're bringing it away. How do you resist something going away from you? Well, you pull it back, right? You try to attract it back. So how do you attract a south pole back towards you? You induce a north pole here, okay? And then by extension, the other side of you becomes a south pole. Okay, now again, okay, now how do you induce that? What do you have to do? Well, let's take our thumb, our right thumb, point it to north, and sure enough, again, that arrow is showing current, right? So the student is doing a good job so far as long as they meant for their arrows to be current. What about electric field? What about electron flow? What if a student tried to do that? Well, second left hand rule for circular currents, take your left thumb now, it still points towards north, right? In each hand rule, thumb points towards north. And what would an electron do? Well, it's negative, so it would do the opposite of what current would do, and sure enough, that checks out. Okay, this one. How do you resist a north pole going away from you? Well, you try to attract it back. How do you attract a north pole? With a south pole. Which means on your other end is a north pole. Okay, so let's check the student's work. If that's supposed to be current, seems like they're using current, not electron flow. Right thumb then goes towards north for a straight magnetic field in a circular current. And sure enough, yes, they did it right, right? It's up in the front, would be down in the back. So good job, student. Now over here, what's happening? A south pole is being brought closer. How do you resist something coming closer, you push it away, you repel it away. And again, how do you repel a south? With a south. So on this side, a north. Okay, let's check the student's work. So if they were doing current, they would take their right thumb, point it north, and sure enough, yep, they did a good job. Current should be up. Let's just think really quickly again. What about electron flow? What if you wanted to go with electron flow? Would it still work? Well, now you would use your left finger, your left hand, point your left thumb towards the North Pole, and sure enough, yes, an electron flow would do the opposite of what current would do, right? So that would work out both ways. Okay, good. 4 out of 4. Student must have had a good physics teacher. All right, just looking at the next one here. So the direction of the induced electron flow in the current, if it undergoes this change that we're seeing happen to it in the magnetic field, right? So if this is the North Pole here, closer to us, what does that make that pole? You're so smart. The South Pole, okay? Let's just label that a bit clearer, okay? So we are taking a South Pole and pushing it into this circular coil, right? So we're taking right? So we're doing this. How would this ring induce a current in itself so that it could resist that? Well, what's coming towards it? A south is coming towards it, okay? How do you resist a south coming towards you? Well, you push it away. And how do you push away a south? You make yourself have a south closer to it, right? So it's just gonna, we'll say south will be the closer face to us, right? So when we look at it like this face will be south, and that face will be towards the back will be north. Okay, that's how you resist this thing coming towards you. Now, first things first, is this going to be the first hand rule for straight electron flow or the second hand rule for circular electron flow? Well, we're looking for the electron flow in this thing, right? So definitely circular. Okay, so take your, it's electron flow, so left hand, okay, make your thumb be the magnetic field pointing towards north within the magnet, and there we go. So the magnetic field into the page, and therefore the electron flow will go around the coil like this. So from our perspective, that would be counterclockwise. Okay, look at this one. We've got a north coming at us. How do we resist that? How do we stop a north from coming at us? Well, we can push it away. How do you push a north away? With another north. Whoops, usually north has been red. Okay, what does that mean down here? A south. Let's do electron flow and current for this one. So I'll be a current first, okay? If there's a north pole up, that will be my thumb. And what does that mean current is doing? Well, you can see it's gonna wrap around the back. In the back, it's gonna be going to the left of the page. As it wraps around in the front, it's going to be to the right of the page, right? So if I'm current, I'm gonna go around the back, and then current will be that way. Okay, what about electron flow? Well, if I'm an electron, same idea with the thumb, that points towards north, right? That never changed in our second hand rule, but the finger direction definitely does change. So now in the back, it's pointed to the right of the page, and then as it wraps around to the front, it's pointed to the left of the page. So if I'm an electron, I do this, of course, the opposite of what current does, because current's what a positive charge would do. And so since the induced current will always be in a direction so that its induced magnetic field will resist the original change, let's take this apparatus here, okay? This is you see it's just metal, kind of in a circle, and also in a broken circle. So, but again, not a magnetic metal. You can see there's no stickiness there. It's not moving because I'm touching it, right? It's not attracted to the magnet or anything. What it is going to do though, okay, let's watch. So I'm going to, friction has to be low so that it's apparent, okay? Watch this. I'm going to change this magnetic field into this loop of conductor. You see that? I didn't touch it, I promise, right? So why did it get pushed that way? And then when I come back, you can see it comes the other way. Oh, right? When I come back, it comes the other way, or I can come from this side. So why is that happening? Well, let's try and think about this with our hand rule. So I have a magnetic field here that I'm going to change towards this looped conductor here. So what is going on with this magnet? Let's figure that out first. So when I have this magnet, okay, you can see pointed down there, so that must be its south. That must be its south. Okay, so as the magnetic field, a south is coming towards it. A south is coming towards it. So what's it going to want to do? It's going to want to induce a magnetic field that resists that change. Okay, so it's going to want to induce a magnetic field that resists a south coming towards it. How do you resist a south coming towards you? Well, how do you resist anything coming towards you? You repel it, right? So how do you repel a south? You induce a south on this side, the side closer to me. So this side needs to become a south. Okay, let's use our right-hand rule for current. So if this side is a south, our thumb points towards north, right? And that means current must be flowing this way around the circle conductor. Now, do you think it should work on this one where it's broken? Let's see. Doesn't seem to work on this one. So what's the difference? Whoops, I hit it that time. So, well, can current flow if it's broken here? Is there any way for current to actually flow? So when it goes to induce a current that's going to resist that change in magnetic field, there's no actual way for the charges to move all the way around, right? You got to remember this is electricity. It's happening very quickly. So even though, yes, they will kind of make a motion over there, if they can't keep it up, there's pretty quickly that electrostatic force of repulsion builds up and no more charges are going to want to move over there, right? And so this one is not really capable of inducing any significant current to actually resist that change in magnetic field with its own induced magnetic field. Whereas this one, since current can flow, right, that can happen. So notice how it resists the push in, and then it induces to do the pull out, in, out, in, out. Whereas this one over here, nothing because the current can't flow. Pretty cool. Okay, so that honestly wraps up not only chapter 12, but the entire electricity and magnetism unit. So that is kind of the end of the teaching part of it. I am going to post another video, kind of an extra video, going through these last few pages of your chapter 12 notes. I do recommend you try these questions. If you're stuck with them, you can go to that video and see what I had to say about them. They are good. They definitely do focus mostly on this stuff, but there are elements of chapter 10, chapter 11, kind of this whole unit in there. So that I do like that about them. They can incorporate little pieces of this whole unit so far. So try out the questions. I do recommend you go watch that video if you want. But in terms of this week's stuff, that's it. So if you are wanting some practice, you can go try the remainder of whatever the 12.3 and 12.4 for this topic specifically. You can look on the Google Classroom or the agenda for which questions specifically focus on this stuff. And yeah, I won't be posting over spring break. So enjoy, have a great week. I will see you after.